the Cornerstone project in the UK.
Excellent. Okay, very good afternoon, everybody. Thank you for the introduction. My name's Callum Littlejohns from the University of Southampton. I'd first like to thank the organisers for giving me the opportunity to come and speak here today. And also I'd like to thank the previous speaker who very nicely gave a very good application of quantum photonics in a silicon photonics platform. So that is the purpose of my talk. I'm not a quantum photonics guy, so half of the stuff here has kind of gone straight over my head. So I'm not here to present to you any data, rather I'm here to present an opportunity for you to build your photonics devices, systems and circuits into a photonic integrated circuit, or more specifically a silicon photonic integrated circuit. So Cornerstone here is a EPSRC funded project that we've been running in the UK for about 4 years now. And its purpose is to bring silicon photonics to places like here where perhaps you don't have the mass production and scalability for the fabrication. So we offer a silicon photonics fabrication capability. So this is an overview of my talk. I'll just kind of briefly go through what silicon photonics is in case some of you aren't that familiar with it. And then I'll go into the details of the Cornerstone project. So just to define what silicon photonics is, this is a slide I've borrowed from Abdul Rahim, who's a member of EPICSFAB, which is the European Alliance for Silicon Photonics. And they define silicon photonics as the implementation of high-density photonics integrated circuits by means of CMOS processing in a CMOS fab. So this is the key point of silicon photonics. We use existing CMOS technology that is very advanced based on the electronics industry, and we kind of exploit empty space in their fabrication capability. So this leads to very complex circuits at a very low cost. So just to extend on that a little bit more, what are the key selling points of silicon photonics? So as I mentioned, the key driving point is the ability to integrate electronics and photonics together onto the same chip. Now this leads to greater functionality. You can reduce capacitances and things like this, improved performance, and crucially more advanced lithography. So we can use the last 60 years of knowledge that has been built up and then simply transfer it to photonic applications. And actually, more often than not, the photonic circuits are significantly bigger than electronics. Therefore, we don't need the state-of-the-art technology. We can use technology from 10 years ago, and this again leads to becoming very cheap. One of the key points of why silicon, as opposed to other photonic platforms, is that it has a high refractive index contrast. So this means that you can build very compact components. You can enable massive interconnect density by WDM, so wavelength division multiplexing, but this isn't exclusive to silicon. But the bottom one is kind of a key selling point, is low cost. Now a lot of people might associate silicon and low cost only in mass production. That is not only low cost in mass production. With like the development of multi-project wafer services, such as what we offer, the cost is actually pretty cheap, even for very small volumes. So that's the good stuff about silicon photonics. What are the challenges? So this is the crucial one on top. It's an indirect bandgap material, which means there's no light emission. So current silicon photonic technology relies on hybridization of some sort, so we use other platforms for the light sources, and in some cases the detectors as well. And this is obviously quite an expensive process to do. So this is the crucial selling point, crucial roadblock for silicon photonics becoming like a very high volume production. But I should say that technology is coming onto the market now. A lot of products that are on the market rely on off-chip. They keep the light source and the photonics completely separate, and this has many advantages. such as the cost of integration, and also because typically it's the light source that fails before the photonic circuit, so it means that you can keep them separate. So other challenges, I've said here it's transparent in telecoms wavelength, which is obviously very good if you're trying to make waveguides, but it means that there's no detection. So germanium now as a photodetector is becoming a very mature process, and it's available in many of the foundries where you can build silicon photonics. So this is now, over the last 10 years or so, considered a mature technology that is sort of comparable with other more traditional detectors in terms of performance. The third point there, it's a centrosymmetric crystal. This means there's no Pockels effect. So this is what sort of traditional modulators like lithium niobate will exploit. However, maybe that's not the best place to talk about this, but we have carrier-based modulation instead in silicon photonics. So I realise in many of your cases this isn't particularly useful because of the losses it introduces, but this is also now a mature process in silicon photonics. So perhaps the fourth point is useful. The thermo-optic effect is very strong in silicon. Some people might think this is a bad thing, but in terms of the temperature stability of certain components. But what it does mean is that you can very easily shift phase with heaters and temperature. And finally, the high index contrast does make the coupling quite difficult, but now we can get sub 1 dB grating couplers for coupling light onto your chip. But this does need very advanced technology and particularly small features. So most of you will probably associate silicon photonics with the silicon on insulator platform. I've listed here some of the advantages and disadvantages of this particular platform, and many of the foundries there where, if you want to, you can access their technology in this platform. So that's thin SOI. Other foundries, mostly VTT, offer thick SOI. So this is layers thicker than 500 nanometers. This may be of interest for low loss applications. Because the waveguides are bigger, the losses are significantly lower in this type of platform. It also means you can support longer wavelengths and more power. So that's the silicon insulator platform. Now, there are other platforms that we kind of class as silicon photonics as well. Silicon nitride. So this is interesting, the fact that it's very cheap. It's not as complex. The wafers themselves are a lot cheaper to buy. And again, you have very low losses in this platform. But there are yet no good active devices. So in terms of the active devices like modulators and detectors, the thin SOI is usually the preferred platform. So and finally, this is kind of more in the research state, germanium on silicon, which is mostly used for longer wavelengths, mid-infrared, because of the fact that it's absorbing at the telecoms wavelengths. So some foundries, particularly Leti and AMF, who are based in Singapore, they will offer you this platform if you want to build your systems in germanium. So that's kind of the platforms that silicon photonics is, and this kind of neatly compares the different platforms. So I've picked out, well, not me, this is again is a slide from Epic's fab, but we've picked out several different desirable features of a photonic circuit, and we've kind of compared them on a scale of 1 to 5 as to which one's good and which one's not so good. So as you can see on the left there, that's the SOI, the middle one's silicon nitride, and this one on the right is germanium on silicon. And what is hopefully apparent from that is that there isn't one clearly the best platform. So they kind of complement each other. It means there's no monopoly on the best platform to use. So for certain applications, silicon nitride might be the best. In other applications, maybe SOI is preferred. But recently, we have started to see offerings in the foundries where we can actually combine several of these platforms together and kind of exploit the strong points of each platform. So that's very nice. And just a bit of a commercial slide. So this is just to say Silicon photonics is no longer really just seen as research. Over the past 5 or 10 years, there are now products on the market. Several of the big guns are starting to use silicon photonics in their, they're offering products and they're using it in their infrastructure. So this is just kind of an example of some companies that are interested or are offering silicon photonics platforms. So in summary, just the strength of silicon photonics is that we can use CMOS technology, which is very advanced. But ironically, this is also the weakness because we must use this platform. So what that means is that the light sources detectors aren't perhaps as good as they could be in other platforms. But it does mean that we can use the very expensive infrastructure that's already in place. We don't need to rebuild it. So the volumes for silicon photonics are tiny compared to electronics at the moment. So often we'll just exploit like gaps in their production. So if certain foundries run at, say, 90% volume, we can use the other 10%, and everyone's a winner. They get to fill their volumes, we get it for cheap, and we get to use their expertise. So it's kind of a nice platform in that way. So I've mentioned on the previous slide various foundries that you can access yourself. They're open access. Now, us as a research group in Southampton, we used to use these foundries often. But what we were noticing is that what they offer to you, or to us, who don't work there, is that everything is becoming standardized. Now, this obviously has advantages in terms of yields and performance and things like this. But for people like you and me who are trying to do research, it makes the sort of device level innovation particularly challenging because we're not allowed to modify their processes. We can only do what they've already got. So that's where we see ourselves in this Cornerstone project fitting in. So we offer you a bit more flexibility, being researchers ourselves. You can edit our process. We're happy to listen to new ideas you have. So we don't just hide behind IP black boxes and say that's what you get and unplug the phones. We like to listen to you and try to help you in terms of the innovation for the device level. So that's an introduction to silicon photonics. Now I'll go on to what is Cornerstone. So I've already mentioned it's EPSRC funded project. There are 3 partner universities. There is us guys and the University of Southampton. And we focus on wafer scale production. So we, as part of this project, we installed a new deep UV, I say new to us, deep UV scanner, which is a wafer scale industry tool, if you're not familiar with it. It means that we can process 8-inch wafers about this big, about 100 an hour. So we really have mass production capabilities. Obviously we're not really using it for that purpose, but what it does mean is that all of our processes that we share with you are scalable. So we can transfer it to other foundries where they can scale to higher volumes. Also in the project is University of Glasgow up in Scotland, and they focus more on chip level processing, so this might be sort of your very high risk stuff. They use E-beam lithography as opposed to the deep UV projection lithography. And finally we have the University of Surrey, which is in Guildford, just underneath London, and they are ion implantation partners. So that's the only capability we lack in Southampton, but we just send them about an hour up the road to do all our ion implantation there. So just a bit more details about the capabilities. This is in Southampton. There's a nice picture there of our clean room. This is an 8-inch wafer box that this person here is carrying. And this is just a list. I won't go through it, but that's the capabilities we have. The crucial one at the top here is the projection lithography. So like I say, this is an industry tool. Now, this is a 248 nanometer scanner, which is the wavelength of the source, and that kind of determines the feature size you're able to achieve. So currently we limit our feature size that we offer to you guys to 250 nanometers, which in most cases is small enough, but in some examples we can see where it's not. So we also make sure all our processes are compatible with e-beam. So we can offer hybrid processing where we do most of the things on the wafer scale using the deep UV projection lithography, and then for the very high resolution features down to 60 nanometers or below, we can use the e-beam as well. So this sort of mimics the more advanced technology nodes you might access at other foundries. And then there are all the other kind of CMOS processes you would expect. This is just some example devices that we've built in Southampton, so some spectrometers. This is just some cascaded Mach-Zehnder interferometers. Suspended waveguide, so this is the waveguide here, and this is some features, sub-wavelength features we etch so that we can undercut the buried oxide underneath, and this means that you can extend the wavelengths that this waveguide will support beyond 3.8 where the buried oxide would usually be absorbing, and we can support longer wavelengths, which is useful for things like gas sensing, where many gases have absorption bands that are beyond 3.8 microns. So that's passive components, simply waveguides. We can also integrate heaters on top of these waveguides. Here's just an example here of a spiral waveguide with a heater on the top. And perhaps more neatly, we have here a mesh of Mach-Zehders that are each of which is controlled by a heater. And then using this type of circuit, we can actually tune where the light goes through this circuit. I've got a slide on that later if we've got time. So we don't just do passive devices, we can also build active devices, modulators. They are based on carrier effects, as I mentioned before. So maybe this isn't the best room to show this because the loss, you will get some loss from the carriers that you put into these waveguides. But they are very fast. We can do up to 56 gigabits a second using these types of devices. This is just a top view of what we've built in Southampton. This is just on-off keying. We can do more advanced modulation techniques. This is a pretty rubbish eye diagram, I agree with you, but in this case we're kind of limited by the drive electronics. The signal we're putting in isn't particularly great. So using this modulator here and more advanced input signal, we can get over 100 gigabit a second modulation. So this is all accessible as part of what we offer to you through the Cornerstone project in the form of a multi-project wafer capability. And I've got one more slide about Southampton. This is integration, so integration of photonics and electronics together. This isn't actually strictly part of Cornerstone, but we can offer it to you as another service on top. So we can do things like wire bonding. This is bonding an electronic driver to a modulator here. And this is a zoom in of the image I showed you earlier where we got wire bonds to each of these heater pads, and that means that we can control, reroute the light anywhere through the circuit. We can also do flip chip bonding, which removes the parasitic capacitance you see from these wires. So you can bond, say, an electronic chip onto the photonic chip, or maybe even this could be a light source, for example, or things like that. And we do have a team of people who do driver designs. That's just some of the data they've got. Whoops, I pressed the wrong button. That's annoying. Okay, sorry, I'll have to skip all the way through. Right, where were we? Okay, so Glasgow, they have also very similar capability, but everything they do there is on the chip level, so using their e-beam lithography system. And finally, University of Surrey, this is a nice advert for them. They have 3 different ion implanters. There's a picture there on the top right of the periodic table that you probably can't read, but everything in yellow they will implant for you. So that's the beauty of it being a research institute. Probably every element you can name, they can implant. And points if you can get any of the blue ones. So that's University of Surrey, but we don't use their full capability. We only implant boron and phosphorus, which are kind of the standard CMOS processes. Okay, so that is about the project, but what do we offer to you? So we have 3 different SOI platforms. 220, which is kind of seen as the industry standard. Most of the other foundries will offer this. But we also offer thicker SOI, so 340 and 500. We actually think that 340 is a better platform, really. The losses are lower, the active devices are better, but the reason 220 has become industry standard is pretty much just because of the availability of the wafers in the early days. So everybody built libraries in that platform, and now they're too lazy to move to other platforms. But we're giving you the opportunity to do exactly that, and the 500 nanometer platform is useful for a longer wavelength, so mid-infrared applications. It can support longer wavelengths and different polarizations as well. So in these platforms you can build various sort of passive devices, active devices, etc. So we offer it to you in the form of a multi-project wafer service. So if you don't know what that is, what it means is that we share design rules and a set of guidelines for you to follow, and as long as you follow those guidelines you can do whatever you want. And then we take your circuits, we take somebody else's and various other people, we stitch them all together and then we fabricate them all in one go. So it's pretty much a cost sharing mechanism. It means that the cost to you is significantly reduced because you're sharing the cost with other people who are submitting designs. So we periodically announce calls for designs of different types. We have passive calls, which are just waveguides, and that will have up to 3 silicon etch depths. Sometimes, most of the time in fact, we'll add heaters as well, so you can do some phase modulation and tuning of ring resonators, etc., things like that. And less frequently we do offer the active devices as well, which has all of the same capability of the passives, but we have ion implantation steps and metallization for electrodes, and that means you can do modulation. So we do have a website here. If you type Cornerstone and Southampton into Google, you should be able to find us. If you just type Cornerstone, you'll find disposable razors, so maybe that's not what you're looking for, but unfortunately half the population need that, so they beat us on Google. But all of this information I'm sharing with you is all available on the website. It is, I haven't pressed the wrong button this time, it just turned off, there we go. Everything is truly open access. You can go and download this now, so many of the other foundries will tell you it's open access, and then you'll say, okay, can I access it? And they'll say, here's a license agreement you've got to sign. So, you know, is it open access? I'm not convinced. So anyway, feel free to go and download our design rules, our design kits, and all our terms and conditions. Sure. So how exactly does it work? I've already mentioned that we announce calls periodically. We do have a GDS template that you can use, and use whatever software you have that will open that has all of our standard components in. If you want to, we have a partner, Lucida, who have our process design kit built in. So you can, but unfortunately you've got to pay for that, but it is very cheap for academia. They have more advanced sort of capability than just the standard GDS file, so it's very interesting to use that. So after we announce the call, about 6 weeks later, we'll ask you to sign up. This is done online. It takes you about 30 seconds. That's just so we're aware to expect designs from you. And then about 6 weeks later, you have to submit your design, again online, and we will check it for you and say, yep, that's very good. We accept the design. Usually it takes sort of 1 or 2 iterations of design rule checking. So most people will try to push their luck, which we expect, and break some of the design rules. But we do give you a chance to correct some of them. So if you need any support, you can email us. We'll kind of help you with the design as well if you're interested. These are the costs. So if you are from UK academia, it is currently free of charge until September 19. So if you're a young researcher or PhD student, you don't have to go begging to your supervisor for money. So that's very good, but you need to get your act together because it's only until September of this year. after which, unfortunately, you have to pay these prices. And that's just to cover our costs for actually building it for you. And if you're not from the UK, then these are the prices you have to pay, which, thanks to Brexit, are getting cheaper and cheaper by the day as the pound gets more and more worthless. Okay, so because I'm short on time, I'll kind of skip over this, but this is just a little bit about Lucida. Their support is very good. They will offer you training. If you buy their software, you get training as part of the package. So if you're interested, they'll come and speak to you and offer you some guidance on how to use their software. This is just a little table to summarize the standard components. We don't expect you to reinvent the wheel. We have standard components that we're happy to share with you. You can drag and drop them and use them if you like. You can edit them. We don't mind what you do, as long as you fit within our design rules. So this is just a little summary of what we offer. It is in Lucida, or it is in GDS format as well on our website. And this is just the different platforms. So this is more for industry, but you can. We also do offer bespoke runs. So if you have a very niche application that you want, we will listen to your design requirements, but unfortunately you do have to pay for that. We don't offer that for free, whereas the MPW is currently free for you. So just, I'm wary of the time, I better speed up. This is just a summary of what we've done so far. We've had 9 calls that have been fabricated and sent out. Anybody who's submitted some designs, we are hoping for some feedback. It's always appreciated, and not only that, we can also kind of promote your work in our slides as well, which is, helps us. So that's just a summary of the typical single mode waveguide losses we see. It's sort of comparable with what you'll see in silicon photonics in other foundries. But if these losses are too high for you, you can make the waveguides bigger, and the losses will come down significantly, below 1 dB certainly. And I know even here they've measured sort of 0.15 dB per centimetre. So we've had 78 submissions so far from 24 different research groups. So we've got plenty of people who can tell you about what we offer. This is our schedule for this year. It is available on the website if you're interested. As I say, we offer various different platforms on the left, whether it's passive or active. So this is when we'll announce the call, and then you get 3 months to submit your designs. And then it takes us a couple of months to build them for you. Because I've been told I've run out of time, I'll kind of skip over these case studies, but this is just what I showed you earlier. It's inspired by the FPGA, so it's an optical reprogrammable circuit in the form of heaters. This is carrier-based modulation in a mid-infrared, which is the first time it's been demonstrated, we think, in an integrated circuit. The modulation effects are significantly stronger at these wavelengths, which is good for modulation. Maybe it's bad for losses. And this one is O-band, so that's 1.3 micron modulation. So this is our standard design that we share with you, and you can use and do whatever you like with it. So just to summarize, Cornerstone is what we hope is a flexible silicon photonics fabrication capability. Our costs are very low, so low that there's nothing. For now, we offer hopefully fast turnaround times. It is getting better. The design areas we offer to you are actually very big as well compared to other foundries. We have the possibility of hybrid processing with E-beam and deep UV, so that enables you to make very small features. And we do also offer some sort of design consultancy or collaborations if maybe you're not, this isn't really your main field. And perhaps crucially for you guys, minimal administrative requirements. So you don't need to go and talk to your contract office. You can just access us very easily. So just one last slide. If you are interested, we are going to announce this call this week. It's on the 220 nanometer SOI platform, so it's one of the last free to access ones. Just visit the website and you'll get all the information you want for that, and the deadline will be towards the end of June. So with that, I thank you for your attention.
Thank you very much. Does anyone have questions for Callum?
Hi, thanks, that was great. I was just wondering, did Cornerstone have any plans to move to also offer any other materials, like silicon nitride or any Ki2 sort of things?
It's interesting you should ask that, because the answer is yes. We do have plans. Actually, some of you may be able to help us with our plans. We are in the process of applying for additional funding. I didn't plant that question, honestly. And this additional funding will offer silicon nitride on silicon, germanium on silicon, so pretty much all those platforms I showed at the beginning. We do plan to offer that if we can secure funding from EPSRC for a follow-on project. So we do need support, and the more universities that we get support from, the more likely it's to get funded, and then you guys can have that for free, so it's kind of good for everybody, right? So if you are interested in other silicon photonics platforms, send an email there at the top to Cornerstone, and just let us know that you're willing to write a letter of support for our proposal, and it will make our bid a bit stronger. So thank you for that question.
Any other questions? Yes, Josh.
I know we all want to get on with it, so this is a yes or no. Do you have plans to integrate with EPIC's Fab or anybody like that?
Yeah, we are actually members of EPIC's Fab, but it's only it's a consortium of different silicon photonics, so they don't really offer any services. But maybe what you're referring to is Euro Practice, who are sort of the brokers for they're the brokers for many of the silicon photonics foundries in Europe. And again, the answer is yes. We are planning to talk with them and become involved with that. And then that kind of adds, we can talk to other places like Tyndall as well, who offer packaging. So we're thinking about adding that into our capability. And another thing that we want to put into Cornerstone too is the integration of sources and detectors. So drag and drop, like flip chip components. So that is part of the second proposal.
Very exciting, thank you.
Okay, so let's thank Callum again. Thank you very much.